Hello class, and in this video, this will be part 1 of our Unit 4 review. So question 1, I have the probability histogram to the right here, represents the number of live births by a mother 47 to 50 years old who had a live birth in 2012. If a 47 to 50-year-old mother who had a live birth in 2012 is randomly selected, how many live births would you expect the mother to have? So, for this expected value, we are taking the mean of our discrete random variable. That's where we take each value of the random variable times its associated probability. This will be 1 times 0.234 plus 2 times 0.267 plus 3 times 0.169 plus 4 times 0.111 plus 5 times 0.094 plus 6 times 0.035 plus 7 times 0.039 plus 8 times 0.051. You toss that into a calculator, you get an answer of roughly 3.1 as the number of expected live births. For the second question here, I have an investment counselor calls with a hot stock tip. He believes if the economy remains strong, the investment will result in a profit of $60,000. If the economy grows at a moderate pace, the investment will result in a profit of $20,000. However, if the economy goes into recession, the investment will result in a loss of $50,000. You contact an economist who believes there is a 30% probability the economy will remain strong, a 60% probability the economy will grow at a moderate pace, and a 10% probability the economy will slip into recession, and we want the expected profit from this investment. So we're taking the mean of this discrete random variable. This would be $60,000 times the probability of 30% for the economy remaining strong. For the moderate pace one, this was a profit of $20,000 times the probability of 60%. Plus, well, I should probably actually write this as a minus now, since we're talking about a loss minus $50,000 due to the loss if the economy is in recession, and that probability is 10%. If we toss this into a calculator, we get $25,000 would be the expected profit from this investment. For number 3, I have in a game of roulette, a player can place a $6 bet on the number 34 and have a 1/38th probability of winning. If the metal ball lands on 34, the player gets to keep the $6 paid to play the game, and the player is awarded $150. Otherwise, the player is awarded nothing, and the casino keeps the player $6. We want the expected value of the game to the player. So, taking the mean of this random variable, if the player wins, they keep $150. Probability of that is 1/38. But if they lose $6 So we would subtract 6 times. The probability of losing will be 37 out of 38, which is 1 minus 1/38. This will give us the unrounded version to help us with the next part of this question is negative 1.89474. So we would round that answer to negative $1.89 per game. Now, the second part of this wants to know, if you played the game 1,000 times, how much money would you expect to lose? So for this, we are going to multiply this unrounded version by 1,000. So after 1,000 games, or 1,000 tries, you expect to lose this times 1,000 will be 1,000, excuse me, $894.74. After playing that game 1,000 times, you would expect to lose $1,894.74, which not a good amount to be losing. For number 4 here, if we let n be 3, p be 4, we want a binomial probability distribution. And then the mean and standard deviation of this binomial random variable. So we could use the formula for this if we wanted to, right? That formula being probability of random variable x is equal to some number x. This would be n choose x times p to the x power times 1 minus p to the n minus x power. Or the way to do it in StatCrunch very quickly, this would be underneath stat, calculators, and then binomial. Stat, calculators, binomial. And you'll have to do this each time, unfortunately. But what can you do? We have an n of 3, probability of success of 0.4. We want this to be an equals. So if we did 0, we would get 0.216. If we did a 1, we get 0.432. If we did a 2, 0.288. And if we did a 3, we get 0.064. So let me enter all of those into the table for that question. So this is 0.216 for 0. For 1, it was 0.432. For 2, that was 0.288. And then for 3, that was 0.064. And if we were to add these up, we should get a value of 1. So for the mean of this discrete random variable, this is just n times p. 3 times 0.4, this would give us a value of 1.2. The standard deviation of this discrete random variable, well, in this case, the discrete binomial random variable, is the square root of n times p times 1 minus p. So 3 times 0.4 times 0.6 from 1 minus 0.4. This number is about 0.849, a decimal in that regard. Then for question number 5 down here, I have gone to a survey. 65% of matters committed last year were cleared by arrest or exceptional means. 50 matters committed last year are randomly selected, and the number cleared by arrest or exceptional means is recorded. And we want to calculate the probability of exactly 39 of these matters were cleared. So this would be a binomial random variable. Either the murder is cleared or it's not cleared. Each of the 50 murders which were randomly selected are going to be independent. And that probability of 65% of clearing a murder case does not change. So, binomial random variable. So let me hop back up to our binomial calculator. We're going to change this n here to be 50. Probability of success to be 0.65. We want this to be equal to 39. And as StatCrunch here shows us, it's 0.018 in this case. So this probability is 0.018. Part B wants the probability between 36 and 38. So this value, let me open this back up. We're going to the between value here. And we are going to put in a 36 and 38. And changing nothing else. And it's still 50. Probability of success is still 65%. This would give us a value here of 0.154 that rounds to. .154. I want to know, would it be unusual if fewer than 18 of the murders were cleared? So we could certainly go through the process of finding that probability for it, but we do not need to do that for this one. Here we could see that the mean of our binomial random variable is going to be 50 times 0.65, which gives us a value of 32.5. While the standard deviation will be the square root of 50 times 0.65 times 1 minus 0.65, which is 0.35. This gives us about 3.373. And whether or not this is unusual will depend on the values from the mean plus or minus 2 times the standard deviation. Based on those usual values, due to this being an approximation from the normality assumption, since our sample size here is indeed at 50, when we multiply 50 times p times 1 minus p, we get a value greater than 10. So we are good for this. This amounts to 32.5 plus or minus 2 times 3.373. If we subtract, we get 39.246. And, excuse me, that's when we add. Let me do this in order. If we subtract, we get 25.754. And when we add, we get 39.246. The number of 18 and less is less than the lower bound of this. So yes, it is unusual. Since 18 is less than the mean minus 2 times the standard deviation. So that's the first part of this Unit 4 review, and I will see you in the second part for this particular review sheet. Thank you.